Welcome to Microlecture 8 on discerning major versus minor resonance contributors. The key idea here is that not all resonance contributors are equal. Some of them look more like the actual image of what this molecule would look like if we were to go into the lab and measure things like bond lengths and strengths and bond angles. We would see that one or more of the resonance drawings will probably be a more accurate depiction. So how do we tell whether a form is a major contributor and looks more like the actual structure or not? So there's 3 criterion to consider in order, and that is the Octet Rule first, charge separation within the molecule, within the resonance structure, and then lastly, we want to consider the negative charge. Where is it located? Is the formal charge located on the most electronegative atom possible or not? The first criterion to consider is actually the Octet Rule. So if we generate upon finding a resonance form, if we generate a form that violates the Octet Rule, then that is thereby going to be a minor resonance form. And it might be a minor resonance form for other reasons on this list too, but this is a biggie, and so if this one is at play, then hands down we have a minor resonance contributor. So this was an example that we covered in the last video, actually, where we took an isolated carbon-oxygen double bond and just kind of kicked the electrons up onto the oxygen atom, and so that the resonance form looks like this, with a negative charge on oxygen and a positive charge on carbon. Okay, and so clearly the carbon is not bearing an octet here. It has only 6 electrons surrounding it, so it's a minor resonance contributor for that reason foremost. So major and minor. The next reason why a resonance contributor might be considered minor is because it has charge separation. So let's consider this example with nitrous acid and think about, first of all, what is the structure of nitrous acid. So it's an HO bond, and the oxygen is bonded to a nitrogen, which is then bonded to an oxygen. So the structure looks something like this. It does bear resonance, and the electron delocalization looks something like that. So let me go ahead and redraw, but with our electrons delocalized. And so here is the resonance contributor. So as we can see, now we've got some formal charge in this structure that we didn't have in the first structure. So this is what we call charge separation. And it's not just the presence of formal charges that matters, but also if we have formal charges that are spread farther away from each other on the molecule, this is also considered charge separation, and a reason why a resonance form might be minor resonance form. So in this case, the major resonance form is here on the left, and this is the minor resonance contributor. Finally, we have NCO minus, a cyanate ion, and cyanate, when we draw it out, it can look like this. Okay, it can look like this. And in this case, the negative charge is on the nitrogen, or we could have the electrons sitting on mostly on the oxygen atom, giving it a negative charge. Okay, and in this case, the nitrogen has become a neutral nitrogen atom. It has 3 bonds, 1 lone pair, so it's happy. And so would we rather have a nitrogen on or a negative charge on a nitrogen, or a negative charge on an oxygen? So here's the thing. The criterion that we're looking at here is electronegativity of atoms bearing formal charge. If the formal charge is a negative one, we would like that to be on the most electronegative atom. And so clearly, if we looked at Pauling's scale of electronegativity, or we just remember the trend that electronegativity increases as we move upward and to the right on a periodic table, we could justify that this is the major resonance contributor, because oxygen is more electronegative than nitrogen. Here on the left, we have the minor resonance contributor. A good example problem for you to solve on your own. Pause the video, see if you can come up with resonance contributors for H2CN2. Okay, so cyanamide, that's what this compound is. We've got a carbon with 2 hydrogens on it, bound to a nitrogen, which is also bound to a nitrogen. So I might start this structure something like this, giving my nitrogen, my terminal nitrogen, an octet. And then I would notice that this nitrogen here at the end has more electrons than it would like. So it has a -1 formal charge. The nitrogen in the middle has 4 valence electrons, and it would prefer 5, so it's actually a +1 formal charge. And so that is one resonance contributor. We have another one, and that results from moving the electrons on the terminal nitrogen over, and then moving those electrons next door to that over onto carbon. So there's now a lone pair and a -1 formal charge on the terminal carbon. There is still a positive charge on the middle nitrogen, and the terminal nitrogen, well, it has 3 bonds and a lone pair, so that's perfect for nitrogen, and it does not have a formal charge. So here we can see, and these are the only resonance forms that we can come up with here, that we have to analyze whether, these forms bear any extra significance. So does one of these forms look more like the actual structure that we've determined experimentally? So it's true that one of them does, and that's going to be this one here on the left. Think about the reasons why from the previous slide and the criteria that we must consider. And the one that makes the most sense here, since charge separation is the same, of course they're all obeying the Octet Rule, is really just that carbon is bearing a negative charge in one of these structures, and carbon is not an electronegative atom, nitrogen is, and so the negative charge would more accurately be depicted on the most electronegative atom. So that is the reason.